by the way, if somebody, when I'm done, my biggest problem is remembering to turn off the recorder. If you guys will help me remember to do that, that'd be cool. All right. So we'll use transformations of data to achieve linearity. For lines of regression. Least squares lines of regression. To do that, we're going to use logs. Let's review some properties. So log b to the x equals y. You can do this property, IFF, which is math shorthand for if and only if b to the y equals x. So this is the base. Y is the exponent. And x is the solution. All right. What if we have log base b to the m times n? This is log b to the m plus log b to the n. So I kind of remember this one. I think of the exponential rules, the exponent rules. So when you're multiplying two like numbers like a to the third times a to the fifth, you add your exponents, right? So when you're multiplying, you add the logs. It's kind of, they're related, I'm sure. I'm just not one to show the proof for it. And we have log b to the m divided by n is going to be log b to the m minus log b to the n. And the last one, log b to the x to the p power. What we can do is we can bring that exponent, the p, to the front and say this is p log b to the x. Look familiar? A little bit? No? Oh, wow. See, in Algebra 2, we used to teach logs. I don't know what I know it doesn't happen in Math 2. Does it happen? Or I don't think it does. Math 3? Did you guys learn it? Is Math 3? Learn a little bit in logs? Okay. So, and maybe they're teaching it differently now. These are the three main properties that you can use. Common logs. Base 10. And this would be your log, just regular log on your calculator. An example, log 10 to the 1,000 just equals log 1,000. So when we're dealing with log in the calculator, we assume base 10. It assumes base 10 for us. So we don't have to write that base in there. And base E. E is the Neperian constant. I'll get a value here for you in just a second. It's kind of like pi. This is ln, which stands for natural log. And E is about 2.71824, and it's like pi, it goes on forever and ever. You don't really need to memorize this number, because the calculator knows it and uses it, but know that it's pi-ish in its sort of, in its existence. These are natural logs. So logs are kind of funny things. When you're dealing with base 10, any kind of base 10 number, you use log. If you're dealing in any kind of like natural situation, like say, decomposition, maybe human decomposition, if you're, some sort of, maybe an investigator or something like that, or what is that, where they can test the fossil bones and see how old they are. Carbon-14 dating, thanks. You would use base E for that. It's natural sort of occurrences and stuff like that. Strangely enough, like income growth in terms of like an investment also is natural growth. So even though that's base 10 data, it follows a natural growth pattern. So we use natural log quite a lot in math. Well, like I said earlier, I don't, but some people do. All right, so we need to look at an example. On page 271, we're going to look at example 4.5. So in this problem, we have some data we want to put in. And it's talking about Intel predicting in 1965 that the number of transistors on an integrated circuit chip would double every 18 months. This is Moore's law. One way to measure the revolution in computing. Here are data on the dates and numbers of transitions for Intel microprocessors. So I can tell you my first computer was one of these 286s. And to put things into perspective as to how cheap and how much memory things have grown, I built this thinking that I actually had it built in my hometown. There was a company there that was building clone computers. One of the best computers I've ever had, but it was almost $4,000. Could have saved about $1,000. I built it to do CAD drawings, and I ended up never really using it that way. So I had some expensive stuff added that was CAD related, computer-aided drafting. So, back then it had 2 megabytes of RAM, megabytes, right? A 40 megabyte hard drive. It had 2 disk drives, one that was the 5.5-inch floppies, which maybe you guys have never seen except in pictures. The other one was the 3.5-inch. They were harder. They had a plastic harder thing. You still use those? Okay. Had a harder thing, and they were high-density disk drives, which was brand new. Each of the disks held about a megabyte of data. And to put into perspective how much data cost then, it was about $10 per megabyte. So each of those disks were about 10 bucks. And the hard drive for 40 megabytes of hard drive was about $400. So what can you get now for 100 bucks? What, 3 terabytes or something like that at Costco? So things have changed greatly. And, just way cheaper and a lot bigger. I don't know that it's always better. Sometimes I question that, but so what we want to do with this is we want to put the date and the number of transistors in our calculators into our list. So since our date goes up to 2000, if you put in like the last 2 digits, for 2000 you'd have to make that year 100. You could do that if you wanted to cut back a little bit of the plugging stuff in, but I'm going to go ahead and put the full date in. Oh, what am I doing? That's not my list. There we go. By the way, that almost $4,000 computer was not the fastest thing I could buy at the time. It was just the fastest thing I could afford to buy at the time. Oops. Alright, so once we get that data in, let's just take a look at the graph. I'm going to see if everything's cleared out there. And I want scatter plot L1 and L2. And we'll zoom 9 so we can see that guy. And it looks just like the picture they give in the book. So what kind of a pattern do you see in the scatter exponential growth. So it'd be something like, I don't know, 2 to the x or whatever, some base number to the x power would be our function for this. So clearly not linear, right? So we have a problem. We can get the r value. So here's what we're going to do. Let's go ahead and do our stats on this. So I'm going to go stat, calc, line reg a plus bx. Let's see, L1, L2. Let's store the regression equation. So that's vars, y vars, function, put it into y1, and then we can calculate. So my line of regression is y hat equals, wait a minute, this is weird. I need to look at my data real quick, because my notes don't match. That looks good. Well, that's alright, I'm going to go with it. Did you guys get a y-intercept of negative 0.174 or negative 1748, something really big? Okay, alright. My previous work must have been wrong. That's a whole number. That's a big one. Let's add into the trillions, no, billions. Plus 884,184 point, I'm going to say 9x. Y-intercept's the same. I wonder if I didn't put the years in as a whole, the whole number when I did that originally. Perhaps not. Okay, and then I'm going to make note about r squared and r. So r squared is 0.501, and r is about 0.71. And my pattern looks like this. So what does the r squared and the r tell us? What have we learned about those values? If our r is greater than 0.7 and our r squared is 0.5 or more, then we can say it's roughly linear, except what does the graph tell you? It's not, right? It's not. We can't just go with what the calculator says. We have to use our assessment tools of this. It's clearly not linear, even though we get some values that sort of indicate that maybe it is. And if we graph this, we can see what the calculator is trying to do, but it's really not matching the data. So here's what we're going to do. Our exponential pattern this is a form of the equation, is y equals a times b to the x. So here's how I think of this. The b is the rate of change. The x is how many times we make the change. And the a is, well, it's an adjustment to make it all work out for us. If we're writing the equation. And keep in mind what we're really probably looking at here, since it's stats, is this would be a y hat value, not a y value. So, what are we going to do with this? So we're going to take the log of y, or y hat, equals log of a times b to the x. So we're taking the log of both sides of the equation. And on the right side, we can simplify this a little bit. We can say that this is log a times log b to the x. So that was the first property that we took notes on. And then this b to the x, I can bring this x forward and write this as log y hat equals log a plus, this should be a plus here, my apologies, plus x log of b. And the advantage to that is this now puts us into our linear form of y hat equals a plus b x. That's the sort of the formula version of making the change. Lovely, yes? Okay. So what we're going to do is we're going to change our data by taking the log of the transistors. And then graph. I'll need to switch to another page for that. So, going back to the calculator, before I go to the next page here, go to my stat, edit. So the transistors is our L2, and we want to take the log of that. It's far easier in the calculator than it is on paper, okay? So we'll go up to L3, and we're going to literally take and log, so log is on the left side about 2/3 down, and we're going to take the log of L2. And then press enter and you'll get those values. Okay. Is everybody successful at that? Yeah. Okay. Now, next thing we want to do is we want to take and do our line reg a plus bx with L1 and now the new log values, the L3 values. So I'm going to go to stat, calc, line reg a plus bx, and change my L2 to L3. I do want to store the regression equation. So vars, y vars, function. We'll put it right there in y1 where we had the last equation. We don't need both of them in there. And calculate. And I'm going to write some of this stuff down and then draw a quick graph when I get it. So now I have y hat equals negative 280, about 0.5, plus 0.144x, give or take a little bit. And r squared is pretty good. And r is even better. So before we even look at the graph, looking at the r and the r squared values, what can we say about the data now that we've taken the log? Pretty linear, isn't it? I mean, it's almost perfectly linear. So let's have a look. Oops, I need to go into my stat plot. I do need to change L2 to L3. And then we'll graph that guy. That doesn't look right. We'll zoom 9 that. There we go. We have an almost perfectly linear transformation. So now what we have is years and transistors. Yeah.
How does that work if it was non-linear before, but we're still showing it?
Well, keep in mind what we're trying to do is we're trying to predict. So we could use this line of regression to predict how many transistors there were in, say, I don't know, a year that we don't have in here. I don't know if 1990 is one of them or not. Let's say 1990. You could potentially use this to predict out to, say, maybe 2005 or something, because our data ends in 2000, although at that point our prediction might get a little sketchy. But what you'd have to do is, once you got that log value on the straight line, you'd have to transform that back to the real value by taking the anti-log of that value. Does that make sense?
Yeah.
So because we now have a linear model, we can make much better predictions, if that makes sense. Yeah, good question. The question was, how do we, what does that do for us, essentially? Okay, so there is also something called a power law model. Let's take quick notes on that. Actually, before we do that, in example 4.5 that we just did, we have y hat equals a times b to the x. And in this particular case, the exponent was unknown. And because the exponent was unknown, we were able to just simply take the log of y. Okay, we were just simply able to take the log of y. There's another situation where it's called a power law model. Where y equals ax to the p, where in this case the base is unknown. In this situation, we take the log of both the x and the y values. play with this here in just a minute, but here's my thought on this. After trying just the log of y, here's how I would do this. Try seeing if taking the log of both x and y strengthens your linear model. Again, I'm not the world's strongest log guy, but this is what I've found seems to work pretty well. So instead of manipulating algebraically all this stuff, manipulate it in the calculator. So let's just play with this data real quick while we have it in the calculator. And we'll see if a power law model makes it stronger. Now, I doubt that that's going to be the case because we have really strong R and really strong R squared values here, right? But let's say that they were a little less strong. Here's what you would do. You might test the power log and see if that was the case. So if I go into my edit, and I'm going to go to L4. Now what I'm going to have to remember is that L3 is my y logs, and L4 will be my x logs. So I'm going to take the log of my x values, which are L1. So far so good. And then we're going to go through the same steps to get the line of regression. So I'm going to say, go to Stat, Calc, line of regression a plus bx. Now in this case, my x list is going to be L4. L3 is y, that's okay. Store the regression equation? Yeah, I think so. Vars, y vars, function, calculate. Boy, it didn't change much. Let's have a look at the graph, but my R squared value dropped, or did it? Because I would have rounded at the same spots. Yeah. So let's look at the graph. So I got to change X list to L4. And then graph it. And then zoom 9. There didn't seem to be a change at all. Yeah. Yeah. So it worked out either way in this case to be the same. What you want to do is you want to do the log of both if you get something that you think is less strong than it could be. You should get some really good linear patterns with the problems that you'll mess with today. Does that help get us through some logs? Take the log in the calculator, right? I do think that this will turn up on the AP test. I don't think it's going to be a huge part. I think it'll be unfortunate if it's a essay question, but it could be. So we want to make sure we get it covered. Right. So